In this video, we're going to go over acid-base titrations. And we're going to start with what is a titration. So let's say that you have some basic solution of unknown concentration. We can call that the titrant. Let's say you have an acid of known concentration. And what you can do is you can slowly add your unknown base to your known acid. And eventually, you're going to get to some point, and we're going to look at this graph. So we start with our acid, you add your base, you're going to get to some point where the amount of acid equals the amount of base. That is your equivalence point. And using an ice table, you can then work backwards to determine what was the concentration of your unknown base. That's because at the equivalence point, the moles of your acid are equal to the moles of your base. Since your acid would be a known concentration, you know how many moles of acid you have. With this instrument, you can measure what is the volume of base that you added. And since you know the moles of base you added, you can find out the molarity, because molarity is just moles divided by liters, right? But you need some kind of indicator to do this. So a common indicator for undergraduate labs is just a color indicator that changes color when you reach that equivalence point. Now let's say that you have a weak acid and a strong base. What would a titration look like? How would you calculate the pH? So let's just say you have a solution of weak acid to begin with. Well, your initial pH here, you just calculate using an ice table in the Ka. It's an equilibrium problem. We've done those, so nothing new there. Okay, now you start adding your strong base. What would be the pH of your solution? Well, since you have a weak acid, this is going to act just like a buffer now. Your strong base is going to react with your weak acid and create its conjugate base. Since you're creating conjugate base and not OH and not H3O plus, the pH isn't going to change all that much. To determine the pH in this region, you're going to use the Henderson-Hasselbalch equation, which is pH equals pKa plus log of base divided by acid. Then, at some point, you're going to reach the equivalence point. That is, the amount of base you added, your NaOH, equals the amount of acid you started with. And so at this point, you have to ask yourself, what is in solution? Well, all of your strong base has interacted with all your weak acid. Therefore, all you have left in solution is your weak conjugate base. This is just an equilibrium problem then. You can calculate the pH using the Kb of your weak base, and you should know the Kb because you know Ka. Remember, Ka times Kb equals Kw. Use an ice table and figure out the pH using the Kb. 4. If you continue to add base after the equivalence point, the amount of OH minus you have from your strong base is going to dominate your weak base. So you just calculate your OH minus based on how much strong base you just added. And 5, as I just said, once you're past the equivalence point, only care about your strong base. Your weak acid, your weak base are now being dominated. Their contribution is minimal, so only use your strong base to calculate pH. What happens if you're doing a polyprotic acid? Well, here there's actually going to be 2 equivalence points, maybe even 3 equivalence points. So let's say that you have H2SO4, right, with NaOH. That's where you're titrating, right? You're adding NaOH to your H2SO4. So your first Ka is going to be this first hydrogen that comes off, and it has a certain equivalence point with it. Your second equivalence point is going to be the second acidic hydrogen that comes off. So what you see is that you actually have two titration curves. Now, where this first peak, that'll be due to the pKa of Ka1. So it's weak acid Ka1. Your equivalence point here, that's going to be, okay, I used all my Ka1 here. So all I have is my conjugate base for Ka1. What's the pH there? This part is a buffer problem with your Ka2. Second equivalence point, I just have my conjugate base of Ka2. Then up here, it is just my strong base. So when you're dealing with a polyprotic acid, just imagine you're doing two titrations, right? If you're doing two titrations, then each part you should be able to know how to do with some practice. So it may look more complicated, and it is a little more complicated, but the math, it's the same logic, the same steps. Now, I said we're going to use a color indicator in the lab, but another thing we could do is to use an electronic indicator, and this uses a pH probe. And here, all you have to do is just watch the pH instead of the color. And this is much more precise because let's look at our color indicator. Our color indicator goes from white to purple at basic conditions. Now, if you get a deep color purple like this, you can see on the graph, oh, we already overshot our endpoint, and our calculation is going to have some error. It is very hard to get a faint color change like this, so it's much easier if you just measure your pH on the graphs. Because if you measure it using this instrument, you're going to get a nice line like this. It doesn't matter if you overshoot your line, because you can still pick your equivalence point from the graph that you make. So if possible, you will always want to do a pH titration using a pH probe so you can watch the data in real time. However, this might not always be practical, so you can still do it with using a color change indicator. The color change indicator does have some drawbacks though. And that's it for this video. I will see you in the next video.